Good evening, everybody, and welcome to BrisScience for September 2024. My name is Joel Gilmore, your MC for this evening. So excited to be here. BrisScience is brought to you by the University of Queensland, where we aim to bring not just the best scientists, but also the best communicators to share their work and their passion with the audiences of Brisbane, and of course everybody watching this online and on YouTube afterwards. I would like to start, of course, by acknowledging the traditional owners of the lands on which we're meeting and pay my respects to elders past and present. We recognise the deep history that the First Nations people of Australia have, the connection to the land and also to the skies, and some of their astronomical observations are still informing our understanding of deep history today. So, if this is your first BrisScience, welcome. Thank you so much for coming along. You've picked a great evening, first day of spring. 36-degree weather on the weekend, fantastic. Climate change, hey? If this is your first time, a few bits of housekeeping. First of all, if you've got a mobile phone, now is a great time to turn it to silent. Everyone check your phones. Last month we had someone who felt very guilty. But don't turn it off, because we are going to take questions after our talk through the app. So we've got a QR code that is going to come up on the screen right now. So close. There it is. So if you scan that QR code, it'll bring up a Q&A form. Put in the questions during the talk if you'd like, or at the end we'll have some time and we will get to as many of those as possible at the end of the talk. Afterwards, we've got some food and drinks out the side. We all are going to go out the side because the edge is still open till late, so we're kind of just keeping our BrisScience crew here. And we'd love for you to hang around, discuss what you heard tonight, maybe have a chat with our presenter, and of course amongst yourselves, and really savour everything that Brisbane has to offer in terms of science and culture. All right, so tonight we are searching for massive black holes. No, for once we're not talking about the federal budget, but rather the remnants of stars. And for a long time, there has been a certain size of black holes that has been very difficult to discover, more elusive than the ex-Twitter marketing policy. But that might change now after tonight's talk. So tonight, I'm very happy to introduce Professor Holger Baumgardt from the University of Queensland Faculty of Science. He specialises in the study of dense star systems, like the centres of galaxies. He has experience all around the world, so tonight, for what I'm sure is going to be a stellar presentation. Yep. Thank you. Please put your hands together and welcome Holger Baumgardt.
Yeah, okay. Welcome, everybody. So I hope you can hear me. Yeah, okay. So my name is Holger Baumgardt, and today I want to talk a little bit about what astronomers have done, and also what I and my collaborators have done to find so-called intermediate mass black holes. Okay, but before I come to that, so first maybe a few words. So what are black holes? So in principle, black holes, they were first predicted by Einstein's theory of general relativity. According to Einstein's theory, so any object which has mass is starting to bend the space and the space-time around this object. And the more mass you add to an object, the stronger this bending becomes. And if you keep adding mass to an object, at some point you will reach the point where the bending of the space-time becomes so large that not even light is able to escape from that object. So therefore, to an outside observer, such an object would appear to be completely black, because no light from it can reach the observer, and so therefore astronomers are calling these objects black holes. So when Einstein invented his theory about 100 years ago, these black holes were complete speculation. So nobody really knew if they actually exist in the universe. But since Einstein's time, astronomers have obtained many observational data which actually shows that these black holes do also exist in nature. And so one type of black holes which astronomers have found are these so-called stellar mass black holes. So these stellar mass black holes, they are basically believed to form as the end state of massive stars. So if you look at the star like our sun, I mean, we believe in about 5 billion years, our sun will turn first into a red giant. Then it will start to lose its outer envelope and form a so-called planetary nebula. And then in the end, it will end up as a white dwarf. So a relatively compact star, but still not a black hole. But then on the other hand, if you look at more massive stars, so stars which have about more than 20 times the mass of our sun, so their life is much more dramatic. So for these stars, they also turn into very large giants. But then at the end of their life, they get completely unstable. They make a huge supernova explosion. And then for the most massive stars, a black hole should form. And astronomers can indeed see a few of these black holes which have formed out of these massive stars. So the way these stellar mass black holes are found is basically there are two ways. So first is, I mean, okay, the black hole itself is invisible, but if you have a star which is very close to this black hole, then the black hole is sometimes able to accrete some gas from that surrounding star. So that gas is then slowly spiraling into the black hole, but as it does so, it starts to heat up a lot and it starts to shine. So therefore, astronomers, while they can't see the black hole, they can see the gas falling into the black hole and then conclude, okay, in this place there has to be a black hole. So that way, about 20 or so black holes have been found. But then there's also a second way by which these stellar mass black holes have been found, and that also goes back to general relativity, because when you look at massive stars which can form black holes, many of these massive stars, they're actually not alone. They have a partner, which is also a very massive star. And so then what is happening, so both of these stars do their stellar evolution, so they turn into giants, then make supernova explosions, then turn into black holes. So what you get from these binaries is then basically a binary of stellar mass black holes. And then there's also a prediction from general relativity. If you have such a binaries and you have two black holes which are in orbit and go around each other, they again start to influence their surrounding space. And due to the motion of the two black holes around each other, the surrounding space is slowly compressed and also expanded, which is happening at the same time scale as the orbital period of the black holes. Yeah, so therefore these black holes, they do emit so-called gravitational waves. And while these gravitational waves are emitted, this black hole binary here is starting to lose energy, and therefore the black holes get closer and closer to each other until at some point they merge. So that is also a prediction of general relativity which should happen, and astronomers really were working hard trying to find these gravitational waves. And so in 2015, they actually succeeded by using a building a gravitational wave telescope which was called LIGO. So the idea of LIGO is basically that you have a very strong laser which shines light into your gravitational wave detector. Then you use a mirror here, which reflects half of the light in this direction, and the other half of the light can pass through. And then you put two mirrors at the end of this light beam and reflect the light back. And then you combine both light beams again and look for a signal. And now if you have a black hole binary up here, which is in the process of merging and emitting gravitational waves, then these gravitational waves will travel through your gravitational wave detector, and they will slightly change the distance between this light splitter down here and the mirrors up there. I mean, these changes are extremely tiny, and so therefore it took a long time until one could build such a detector which was accurate enough to be able to detect these changes. But since 2015, astronomers have been able to detect the inspiral of these stellar mass black holes in about a few hundred cases. And I mean, one such example is also showing here. So I mean, this LIGO detector, there are two actually in America, one in Hanford and one in Livingston. And here you see basically how the distance between these mirrors is changing as a gravitational wave is passing through. And both of these detectors are able to detect the same signal. And so therefore we know, okay, there is a black hole binary out there somewhere which is in the process of merging. Yeah, so therefore these stellar mass black holes, they are really pretty well established. We can be relatively sure that they exist. And we also know the masses of the black holes which are in these stellar mass black holes. They typically have masses of a few solar masses up to about 100 solar masses. So I mean, this is one type of black holes which astronomers have been able to find. Yeah, and then comes the second type of black holes. These black holes are called supermassive black holes. So these supermassive black holes, they have masses somewhere from 1 million times the mass of our sun up to about a few billion times the mass of our sun. So these are really humongously large black holes. But astronomers believe that basically every large galaxy, like our Milky Way, does have such a supermassive black hole in its center. Yeah, and the strongest evidence for these supermassive black holes actually come from observations of our Milky Way itself. And so for that, I have here a movie which shows what astronomers have found when they were looking into the center of the Milky Way. So, I mean, that movie starts basically with an all-sky view of the Milky Way. So, I mean, if you just go out at night and you're in a relatively dark location, then you can see the band of the Milky Way going across the sky. And now I can start the movie. And in the movie, we will start to zoom in into the center of the Milky Way. So now we are getting closer here to the center. At some point, we need better resolution, so we have to change the telescope that we are using so that we can see the stars in the center. And we are zooming further in, and again, change to another telescope, and then go back to the very center. So I mean, here now we are looking at a region which is about 100 times the size of our solar system. And so as you can see, I mean, astronomers can still see a few stars. And the interesting thing is these stars are moving. And they are moving actually very fast. So when you look at the stars, and especially at the innermost stars, I mean, you not only see them moving, but you start to see full orbits of these stars. So these stars are clearly moving around an object which is sitting in the middle of this star cluster. But the object itself is completely dark. And so I showed it maybe so from the halfway point again. So here you see the stars moving, and you see, when you look at individual stars, that they are really, you can see one full orbit that the star is making. And so what one can do is, once one knows in which kind of orbit the star is, so one knows the orbital period, and also the size of the orbit, one can basically calculate, so how massive does the central mass be in order to make the star move in the way we see it moving. And the result basically for all of these 10 or 15 stars in the central cluster is that one needs an object sitting in the middle of them, which has a mass of about 4 million times the mass of our sun. And so that is a huge mass. So I mean, normal stars only have masses up to 100 solar masses or so. So therefore, such a massive object cannot be a star. And since this object is also completely dark, that means basically in the center of our Milky Way, there has to be a massive black hole sitting. Yeah, so I mean, that is basically the evidence that we have for a massive black hole in the center of our Milky Way. And I mean, so this evidence is basically so strong that back in 2020, the discovery of this black hole was awarded a Nobel Prize. So, I mean, Reinhard Genzel and Andrea Ghez, I mean, these were two observers who discovered this black hole. They got one half of the Nobel Prize. So the other half was given to Roger Penrose. He made theoretical calculations about black holes. Yeah, so I mean, that is basically the evidence that we have for a massive black hole in the center of our Milky Way. Then one might ask, so what about other galaxies? And I mean, indeed, astronomers have found massive black holes also in about 20 to 30 other galaxies. And so, I mean, this plot here basically shows the results of all these black hole discoveries. So down here, we have the mass of the galaxy in which the black hole was found in terms of the Milky Way mass. And up here we have the black hole mass. So going from something like 1 million times the mass of our sun up to about 10 billion times the mass of our sun. So I mean, all these black holes which astronomers have found, I mean, they are first extremely massive. And secondly, they also show a relatively good correlation between the mass of the black hole itself and the mass of the galaxy. So the more massive the galaxy itself is, also the more massive is its central black hole. Yeah, so therefore one can in principle summarize what astronomers know about black holes and their masses in a diagram like this. So down here we have the mass of the black hole, and so going from 1 solar mass up to a million and more massive. And so basically all the discovered black holes that we have found so far are either down here, so less than 100 solar masses, so that means this is the stellar mass black hole regime, or they are more massive 1 million solar masses, so that is the supermassive black hole regime. But the problem is that in between these two regimes, there is a complete desert. So between 100 solar masses and about 1 million solar masses, there is absolutely no discovery, or there was no discovery until last year. So, and that, I mean, was really quite a large problem, because, I mean, first of all, when we look at this diagram, so the lowest mass supermassive black holes that we have found are about 1 million solar masses. But, I mean, this limit down here, this is just driven by observational limitations. I mean, trying to find a black hole in a faraway galaxy is a hard thing. And the less massive this black hole is, the harder it gets. Because a light supermassive black hole is only having a very weak influence on its surrounding stars. So it gets very hard to discover black holes down here. So therefore, I mean, while the observations end at 10 to the 6 solar masses, there is no reason to assume that there would not be also some less massive supermassive black holes. And the second reason why this desert here, this no detection in this range is a problem, is also when one thinks about, so how did these supermassive black holes actually form? So why do galaxies have so massive black holes in their center? I mean, the most natural way how to form a supermassive black hole is basically one can start with a stellar mass black hole, because these we know how they form. I mean, you just need to start with a massive star and you get a stellar mass black hole. And then maybe if one has such a stellar mass black hole back in the early universe, then I mean that black hole can have started to grow in mass. So it might have just swallowed some stars which came too close to it, or it swallowed some gas or so, and then it increased in mass until it became a supermassive black hole. So that would be the most natural way how to form supermassive black hole. But if that is the case, then one would maybe expect that, okay, many of these stellar mass black holes made it all the way into the supermassive black hole regime, but there should maybe also be a few of these stellar mass black holes which started to grow in mass, but then they suddenly stopped. Maybe because there were no stars around them anymore, or there was no gas. So they stopped somewhere in the intermediate mass black hole regime. So the natural expectation is if supermassive black holes formed out of stellar mass black holes, then intermediate mass black holes should also exist. And given the fact that none have been found, so there have actually also been astronomers who have speculated that these supermassive black holes, maybe they formed in one go. So maybe in the Big Bang, somehow the universe in some places started to collapse and formed a supermassive black hole out of nowhere. Yeah, so therefore there are different ideas how supermassive black holes could have formed. And so therefore, in order to decide what is really going on, it is really necessary to find intermediate mass black holes. Yeah, and that was basically something that we tried to do. So then, I mean, the question is, okay, if one wants to find an intermediate mass black hole, where can one look? Well, I mean, in principle, one can use this relation here as a guidance, because that relation tells you that the less massive the galaxy is, the less massive the black hole in it is. So that means if you want to find black holes down here, you have to look at small galaxies. And so that means one needs to look at so-called dwarf galaxies. Yeah, so these dwarf galaxies, I mean, they are quite numerous in the universe. So basically, every large galaxy like our Milky Way has a swarm of these dwarf galaxies which are orbiting around it. And in case of the Milky Way, there's actually one very interesting dwarf galaxy, which is called the Large Magellanic Cloud. So the Large Magellanic Cloud, that is a galaxy which is well visible from the southern hemisphere, so also Australia. So maybe some of you have already seen it. It has about the mass of 1/10 of the Milky Way, and it is about 150,000 light years from the center of the Milky Way. And so therefore we tried to see, can we find an intermediate mass black hole in the Large Magellanic Cloud. So what we did is we had a look at the center of the Large Magellanic Cloud. So there is a point here around which the stars and also the gas in the LMC are moving around. So roughly here is the center of the LMC. So therefore what we did is we looked at the velocities of the stars in the center, because so that was the way how the supermassive black hole in the Milky Way was found. I mean, people just looked and they found stars which were moving with very high velocities. But I mean, the result of our search, so that is shown in this diagram here. So blue, these are stars which are coming towards us, and red and yellow are stars which are moving away from us. So what our observations very clearly showed was, I mean, that the stars in the Large Magellanic Cloud, they are rotating. So, I mean, this side down here is coming towards us. The upper side is going away from us. But what our observations did not show was anything unusual happening in the center. So, I mean, the velocities of all the stars there, they were still relatively low, only of the order of 10 kilometers per second or so. And these stars simply participated in the general rotation. So, therefore, there is no evidence that there would be a massive black hole in the Large Magellanic Cloud. And the same result was also what other people found for other dwarf galaxies. So therefore, I mean, the searches for massive black holes in dwarf galaxies have so far not turned out anything. So it doesn't mean that they don't exist, but it just means maybe if they are there, but they are just not massive enough so we can detect them. So therefore, if we want to find massive black holes, we need to look somewhere else. Yeah, and so therefore, we also started to look, and also other astronomers started to look in another place. And the second place where people have looked for massive black holes, these are so-called star clusters or globular star clusters. So globular star clusters, I mean, they are, as the name says, star clusters. So they are made up of thousands to millions of stars. So these globular star clusters are usually quite old. They are typical ages of about 13 billion years. So that means the stars in these globular clusters, they have ages comparable to the oldest stars in galaxies. Yeah, if one looks in the Milky Way, so the most massive and brightest globular cluster is Omega Centauri. And you can see an image of that cluster here. And Omega Centauri is actually also quite an interesting cluster, because there are many hints when one looks at the stars in Omega Centauri, which show that when Omega Centauri formed, it actually did not form as a normal star cluster, but instead it formed inside a dwarf galaxy. And most likely Omega Centauri was actually the center of this dwarf galaxy. So nowadays, when one looks at Omega Centauri, one does not see the surrounding dwarf galaxy anymore. So what has most likely happened in the early history of the Milky Way was that this dwarf galaxy fell into the Milky Way, and then due to the strong gravitational forces from the Milky Way, this dwarf galaxy was disrupted. So the Milky Way was permanently tearing away stars from the dwarf galaxy, and the stars were then later spread all over the sky. So that dwarf galaxy is gone and is basically cannot be seen anymore. But the center of that dwarf galaxy, Omega Centauri, that has survived because it was the densest part of the galaxy and was therefore not torn apart. So therefore Omega Centauri is nowadays moving around the Milky Way just as a single cluster. But as we have seen, I mean, we know galaxies contain massive black holes in their centers. So therefore, I mean, it is quite natural to assume that there's also a massive black hole sitting in Omega Centauri. And so therefore, astronomers have already, since about 20 years, started to look, can they find a black hole in Omega Centauri? And so one of the early works that was by Eva Noyola and her collaborator. So she looked at the velocities of stars in Omega Centauri and plotted these velocities as a function of the distance from the center. So what she saw was, of course, that in the outer parts of the cluster, the stars move relatively slowly. But then when you go towards the center, the velocities of the stars are permanently going up. So the more you go in, the faster the stars move. So that in itself is not unusual. This is actually what one would expect. But the surprising thing was, if one, when they compared the observed velocities with the velocities which one would expect, if everything, only the visible stars, that is all what there is in Omega Centauri. So then one gets a predicted velocities curve, which is down here. And so there, as you can see, in the outer parts, one can explain the velocities, but in the inner parts, the expected velocity is only about 15 kilometers per second. The observed velocity is almost 25 kilometers per second. So the stars in the center, they are too fast. And what that means is, so there has to be some additional mass in the center here, which keeps the velocities up. And so that was something that they have modeled. So they started to throw in massive black holes of different masses, and they found, okay, if one has a black hole of about 50,000 solar masses, or 40,000, then one can explain these velocities. So therefore, they thought that they had found a massive black hole in the center of the cluster. But unfortunately, then we came along, and also other astronomers, and decided to take a more careful, first do more careful measurements. So this is our data. So of course the velocities are still increasing, but then they start to level off at some point. And then we also did more careful modeling, because when you look at Omega Centauri and you think about that cluster when it was formed back 13 billion years ago, at that point, Omega Centauri had the visible stars that we see nowadays, but also lots of massive stars. So these massive stars, they have died away, but they have formed stellar mass black holes. So therefore, one expects, in addition to the visible stars, that there are also lots of stellar mass black holes in Omega Centauri. And if one tries to predict the velocities of the stars, one has to take these stellar mass black holes into account. And so that was something that we did, and then we found, okay, you can explain the observed velocities by a black hole, intermediate mass black hole, but you can also explain it by a cluster of stellar mass black holes. So therefore, the observational data that we had, was simply not good enough to distinguish between these two possibilities. Because if you want to do that, in the very inner parts, an intermediate mass black hole does make a difference compared to a cluster of stellar mass black holes, but we simply have no data here. Yeah, so therefore, I mean, the situation in Omega Centauri at this stage was completely undecided. And unfortunately, that was not only the case for Omega Centauri, that was more or less the case for every cluster where astronomers have looked. So therefore, if you would have asked an astronomer just a year ago to summarize all the knowledge that we have about intermediate mass black holes, the answer would have been blank. We absolutely had no idea, do they exist or not? Yeah, but on the other hand, we need to know it. So therefore, what do we need? We need better data. Okay, and that was now something where my collaborators in Heidelberg started to get in. Because they had an idea to look at the data that the Hubble Space Telescope has obtained for Omega Centauri. Because the Hubble Space Telescope, as many of you might know, I mean, the Hubble Space Telescope was launched into space about 30 years ago. So since then, I mean, it has taken images of galaxies, star clusters, many different kinds of objects, and I mean, it has really been a huge breakthrough for astronomy. But unfortunately, I mean, there is one slight problem with the Hubble Space Telescope. Because, I mean, the Hubble Space Telescope is out there in space since 30 years, and space is really not a very welcoming environment for technology. Because anything which is in space is basically constantly bombarded by cosmic rays. And these cosmic rays, they slowly start to degrade the whole instrument. So therefore, I mean, the engineers which are running the Hubble Space Telescope, I mean, one thing that they really need to do is they have to check how the Hubble Space Telescope is working and what cosmic rays and other things have done to the instrument. So therefore, engineers are constantly monitoring the Hubble Space Telescope. And how do they do it? Well, actually, what the engineers did was they decided that they are going to have a look at Omega Centauri. And they are going to have a look at Omega Centauri every few months, since the Hubble Space Telescope was started. So therefore, over the last 25 years or so, the Hubble Space Telescope has taken hundreds, almost 1,000 images of Omega Centauri. So I mean, so far these images were only looked at by engineers, because they just looked, okay, how does a star that we take an image of now, how does that compare with an image 30 years ago? And then trying to recalibrate the instrument slightly. But basically our idea was, okay, why not use these images and also do science? Because one thing that you can do on these images is, I mean, you see the stars, and therefore you can measure the positions of the stars. And after you have measured the positions of the stars, one can do one thing. One can start to compare these positions, which were, for example, taken 30 years ago, with positions which are taken nowadays. And that is something that you can see in this movie, and now you can see it even more clearly. I have a technical problem here. And what you can see is, I mean, of course, I mean, stars in the center of Omega Centauri, they are moving. Yeah. Okay, all good? Yeah, okay. So therefore, I mean, just by looking at these images, you can also determine velocities of stars. And since the Hubble Space Telescope has such an enormously good resolution, therefore that allows you to measure really velocities of stars with very high accuracy, and also very far or very close into the center of Omega Centauri. Yeah, and so that is basically something that we did. And so this is now the same plot as the previous one. So again, you have models with an intermediate mass black hole and models with a cluster of stellar mass black holes. So now, due to the HST data, we are able to push a little bit further into the center of Omega Centauri. And so one thing that you can see is, now we start to see a rise in the velocities of the stars, which was not there previously. The old data simply had too large error bars. And as you can also see, the intermediate mass black hole model is still fitting the data. Now the stellar mass black hole cluster model is starting to have a problem. Because the problem with a large cluster of stellar mass black holes is this cluster is extended. And since it is extended, it is not able to rise the velocities on very small scales. While an intermediate mass black hole, there all the mass is in one point, and therefore the closer you get to that intermediate mass black hole, the higher the velocities get. So that was already one evidence or indication that there is really an intermediate mass black hole in Omega Centauri. Yeah, and another indication was also when one looks at the velocities of the stars in Omega Centauri and when one looks at the velocities in the innermost area, so 3 arcseconds, that is about a small fraction of a light year around the center of Omega Centauri, and one compares that with the velocities that one sees further out. Well, if there is a cluster of stellar mass black holes, then one can estimate that the fastest moving stars which one should see should move with about 60 kilometers per second. The reason is simply anything which moves faster is unbound and will fly away. And so what we found is, I mean, in the outer parts, yeah, that 60 kilometers or 62 kilometers per second is really almost basically the limit. There is just one star which is faster, but that is, looks to be an unrelated star which is just sitting in the foreground and has nothing to do with Omega Centauri. But in the inner parts, we actually find 7 stars which are above the speed limit. Or another way how one can plot that is one can basically calculate the density of fast-moving stars as a function of the distance from the center. And so in the outer parts, this density is completely constant, and that is actually what one would expect. I mean, from here and there, you see a few stars which are just part of the Milky Way, but not part of the cluster, and therefore moving with completely different velocities. But in the inner parts, this density shoots up enormously. And there's no reason why stars which are just somewhere in the Milky Way, why they should show such an increase. This increase basically means that these fast-moving stars are really part of Omega Centauri. Yeah, and then one can also look, closer look at the motion of these fast-moving stars. And there what one sees is, I mean, there's basically no coherent motion. So you have some stars which are coming, flying towards the center. Other stars are moving out of the center. So again, I mean, that shows that these fast stars are not due to one particular event, maybe a few stars approaching each other and then scattering each other off. If that would have happened, you would have expected they all come from one place also. But that again is not the case. I mean, these stars move just randomly through the center, and that means, again, there has to be something here in the center which keeps these stars bound. And again, when you look, I mean, you see a few normal stars, but one does not see anything right here in the center. So whatever there is, it has to be completely dark. But on the other hand, based on these large velocities, it also has to be extremely massive. And again, basically invisible, but extremely high mass. That is the telltale sign of a massive black hole. Yeah, so therefore, we tried also to model, so what could the mass of that black hole be? So currently, I mean, our data is still not very good to give us an accurate answer because, I mean, we know how the stars move across the sky, but we do not know the velocities of the stars towards or away from us. So therefore, we don't know what are the true velocities of the stars. And another thing that we, of course, also don't know is where actually is the black hole sitting. I mean, it could be right here in the center, but it could also be distributed somewhere around it. And so therefore, I mean, depending on the exact location of the black hole and also the true velocities of the stars, the full velocities, there is still some variation on the black hole mass, but we can put a firm upper limit, a lower limit of about 8,000 solar masses. So if it is an IMBH and there's hardly any alternative, the minimum mass is 8,000 solar masses. But the more likely mass is something like 20 or 30,000 solar masses. Yeah, and so therefore one can basically summarize then our finding by a plot like this. So again, that's the black hole mass. This down here is the star cluster mass and would go over into the galaxy mass here on the right. So I mean, these are all non-detections and there are many more as I've shown. So people looked for intermediate mass black holes probably in 20 cases. So none has produced anything so far, only upper limits, but this is our detection for Omega Centauri. And so this is the first, which is really in this intermediate mass black hole regime. So up here are the supermassive black holes. Yeah, so now we know there is at least one out there in the universe, but probably there are many more. The question is, so where are they, and can we find them? Okay, and with that, my talk is finished. Thanks for your attention.
Amazing. Okay, so we are going to take some questions now. We've got that QR code back up on the screen. While you're putting down your questions, whatever you might have, we are back next month. We're not quite ready to announce the speaker yet, but watch your inboxes very soon. Sign up to Facebook, the mailing list, etc., and you'll get that notification. And then we only have one more talk for the year after that, and it's the first week of November, and we're going to be back for our big science comedy panel spectacular. So if you were here last year, very fun evening. We'll have 2 teams of scientists and communicators and comedians competing for glory and no prizes, which is the best kind of glory. All right, so I might get you to go to the middle of the stage there. And we've got a whole bunch of questions here. So first one is from Mark. How small can a black hole be?
That is also a good question. I mean, so the smallest black holes that we have found, they have masses maybe around 3 or 4 solar masses. But in principle, there is no lower limit. It's only if you form them out of stellar mass black holes, then it's probably hard to get below 2 or 3 solar masses.
Okay. Question from Emerald. With a black hole and a companion star binary system, how is the companion not destroyed during the supernova of the other star?
I mean, that is also a good question. Most likely, I mean, you probably need a minimum distance from that star which goes supernova. Otherwise, your star will be too much affected by the winds which come out of that exploding star.
What's a minimum safe distance?
Minimum safe distance depends
hypothetically speaking.
A bit on your star, but I would say, I mean, probably significantly further away than the Earth. I mean, another problem is, of course, also before a star goes supernova, it goes through a giant phase, and then it becomes really ginormously large. So these very massive stars, they reach a size, if you would put them into the solar system, they would reach the orbit of Jupiter. So, I mean, therefore, anything which is closer than that would anyway merge into one star just before the supernova.
So it's a very cheerful talk tonight.
Yeah.
Okay, Jonathan has a question. Let's come back to Earth. How are the Earth-based LIGO detectors able to maintain such a high degree of stability to detect gravity waves? Would not geological environmental factors make this difficult?
Yeah, they have to be very carefully shielded. So especially the mirrors, which reflect the light back, I mean, they have to be shielded from seismic events. So I heard a talk about somebody from a detector in Germany, GEO. They said, I mean, they could see the North Sea waves crashing on shore in their gravitational wave detector. So, I mean, and they were hundreds of kilometers from shore, but they could see that. So, I mean, the shielding is a massive issue.
Okay. Question from John. What are quasars? Are they supermassive black holes?
Yeah, they are supermassive black holes which are accreting gas from their environment, and for that reason they start to shine with extreme luminosity. So initially, when astronomers looked in the sky and they saw a quasar, they were actually not able to see the surrounding galaxy. So that accreting black hole was hundreds of times brighter than the surrounding galaxy, so they only saw the black hole. And therefore they had no idea what they were looking at.
Right. Okay, well, there's a few different questions here around the theme of dark matter and whether dark matter can form black holes. How do we know the difference between stars going around a black hole and dark matter? Maybe you could Are you up for a little bit of that?
Yeah, I mean, dark matter is also an interesting thing. I mean, dark matter could, in principle, at least contribute to the growth of black holes. So that is also something which astronomers have speculated about. So especially for the supermassive black holes in the center, I mean, they would eat anything which gets close to them, and that also includes dark matter. So, I mean, probably dark matter can't form a black hole directly, for all that we know, but it could help getting, for supermassive black holes to get so big.
Right. So Pei asks, since when was the first black hole found?
Yeah, I mean, okay, the quasars, they are already known since about 1960. So, I mean, of course, at the time, nobody really understood what they are. I mean, some people already speculated that there could be supermassive black holes, but others also had other ideas. So, I mean, okay, the first hint for the existence of black holes basically came from these quasars. Then, I mean, the hint for the existence of stellar mass black holes, that started in the 1970s.
Okay, we've got a lot of questions here, so I'm going to try and get to as many as I can, but we'll see how we go. Let's go for a slightly more personal question. How did you, no, I've just lost who asked it, but sorry, apologies, but the question was, how did you become passionate about studying black holes?
Black holes. I mean, I was always fascinated by them, but I mean, what really drew me into this game, I mean, that was basically a paper which appeared 20 years ago, where people thought they found evidence for an intermediate mass black hole, but I looked at their data and it was immediately clear to me, no, that is none. And so therefore I thought, okay, I mean, I have to write something about it just to show to the community that, I mean, no, it is not an intermediate mass black hole. But I mean, that then got me into a fight with that group. But at some point we really decided, okay, I mean, we are actually both interested in these intermediate mass black hole and we want to find them, so I joined forces.
Sort of sounds like the old thing, what's the quickest way to get the right answer on the internet? Post something that's obviously wrong?
Yeah, you will get lots of answers and maybe at some point you can start to work with people and then really get the right answer.
Okay. Anonymous, their name has disappeared, maybe a black hole took it. If there is a black hole in the middle of our galaxy, is it a threat to us?
I would say no. Because, I mean, we are lucky, we are in the fortunate position, we are relatively far away from it. I mean, it's about 25,000 light years. And, I mean, therefore, so we don't feel this black hole in any way. I mean, you could take it out of the center of the Milky Way, and the sun would still be on its orbit, but it is without really noticing that the black hole is gone. So, I mean, therefore, we are relatively safe. If we would be much closer to the galactic center, then it would be a reason to worry, because as soon as that black hole is accreting and starting to shine, it will also emit lots of radiation and also lots of X-rays, and that could have quite a negative effect.
All right. Mel asks, what is the physical size of a black hole?
Also that depends on its mass. So interestingly, I mean, the massive black hole which sits in the center of the Milky Way has about the size of our sun. So it's about a few 100,000 kilometers across. If you would turn the Earth into a black hole, you would have to squeeze the Earth into a sphere, which is only about 3 centimeters in diameter.
And all of that mass is in that tiny sphere.
Yes. So, I mean, that is really extreme. That was also one of the reasons why physicists also initially thought, okay, I mean, Einstein's theory predicts black holes, but probably they don't exist. It's just too extreme.
All right. So let's now get existential. So Louise asks, what happens when you go into a black hole? And just so that everyone knows, so Pittelin is even more concerned. When you fall into a black hole, would you be more concerned about getting spaghettified or missing your next meal?
Yes. I mean, okay, it is probably not a good idea to go into a black hole. If you have the choice...
That's our public safety announcement for the night.
Yeah. If you have to go into a black hole, I would say choose a supermassive black hole. Because a supermassive black hole, there you have the advantage that, I mean, these are, as I said, they are relatively large. And so therefore, when you fall into it, and you go over what physicists call the Schwarzschild radius, so that is basically the edge of the black hole. I mean, that is something that you could in principle still survive. So I mean, you're probably going to see some interesting physical effects while you're falling into the black hole. But I mean, there is also a catch. I mean, once you're inside the black hole, you basically have to go all the way into the center. And that is probably going to be something which is relatively inconvenient because that black hole is going to put very strong tidal forces on you. And so at some point, you will probably start to get ripped apart by the black hole.
And apologies, there's so many questions, I've lost this one, but the question was, what happens at the center of a black hole? Is there another end?
We don't really know. I mean, the physics as we know it basically break down. So I mean, general relativity would say, okay, everything has to fall right into the center. But I mean, that would mean that in the center you get basically infinite density, and nature tries to avoid infinities for all that we know. So probably some new physics has to come into play in the centers of black holes, but how that looks like, we don't know. So therefore, what is happening in the center of a black hole is so far really unknown.
So our last question then.
Yeah.
If we were to invite you back in 10 years' time, what do you think you'll be talking about? What do you think might happen in terms of technology or discoveries in the next 10 years?
I have no idea. I mean, okay, I can see this slide that I have there. Unfortunately, it's not visible for you anymore. I mean, there is a certain chance that if I would be asked to show the measurements that we have in 10 years' time, well, if we are unfortunate, it looks like this. So one discovery and nothing else, because one has to realize, I mean, astronomers have really looked in earnest for these intermediate mass black holes for 20 years. And I mean, it has taken 20 years just to discover one. So I mean, it might take another 20 years until we discover a second one, but maybe it just takes 1 or 2 years, who knows? I mean, this one here came out of the blue.
Well, what an open research question for all the budding astronomers and or PhD students out there. But for now, could you please join me in thanking Associate Professor Holger Baumgardt for an incredible presentation. And we would love for you to join us for some food and drink out the side. And of course, see you next month. Thank you all. Have a good night.
Okay. Yeah. Good. Thanks. Yeah, well, lots of questions. Good one.